So here's what we've got. The corporation manufactures a high-performance automobile engine product at 2 locations. The cost functions for producing X1 units at location 1, X2 units at location 2 are given by the following equations. So the cost at location 1 is given by 0.05 times X1 squared plus 15 times X1 plus 5,400. That's the cost of producing X1 units at location 1. And C2 is given by 0.03 X2 squared plus 15 X2 plus 6,100. That's the cost of producing X2 units at location 2. And to be perfectly honest, if it was me, I would start writing things in terms of X and Y, because this X1 squared and then finding the derivative of that just gets to be a little bit gnarly. So I would probably tend to say, I would rather write this as C1 equals 0.05 X squared plus 15X plus 5,400. And C2 is 0.03 Y squared plus 15Y plus 6,100. Not necessary, but I think makes things a tiny bit easier. We're also given that the demand function is given by P equal to 225 minus 0.4 times X plus Y. And we're given that the total revenue function is given by, and this should, so what I'm about to write down, actually, we could come up with ourselves if we kind of knew what they're asking for. The revenue is just the price times the number sold. So it's going to be the demand function, 225 minus 0.4 times X plus Y times X plus Y, which they do give us, but that's the idea, right? It's the price you're selling at and the number you're selling. So then they ask us to, here's finally the question, find the production levels at the 2 locations that will maximize profit. And profit is revenue minus your costs. So we're in the typical situation in that we're trying to optimize a function of 2 variables. We're going to write it down. So we're going to substitute in the revenue function and the cost 1 and the cost 2 function. So it's going to be a little bit gross. Feel free to ask for clarification along the way. So our profit function as a function of X and Y is going to be this revenue equation. So it's going to be 225 minus 0.4 times X plus Y times X plus Y minus my cost equation. It's going to be minus 0.05 X squared plus 15X plus 5,400 minus 0.03 times Y squared plus 15Y plus 6,100. Whew. And it's probably, okay. My water tasted weird. It's like did I put lemon in my water? I didn't, but like it tasted kind of like I did. Anyway, it's probably worth simplifying this before we try to find the partial derivatives. So, and even though I've noticed here that right, she kind of just went straight to the, I'm going to show the work simplifying here. So if I'm simplifying this, I've got 225 minus 0.4x minus 0.4y times x plus y. I'll FOIL that out in the next step. I'm going to distribute the minus signs and get minus 0.05x squared minus 15x minus 5,400 minus 0.03y squared minus 15y minus 6,100. Distributing, or sorry, foiling out here, this is going to be a bit much. We're going to have 225x plus 225y minus 0.04x squared minus 0.04xy minus 0.04yx, which is the same as xy, minus I kept, oops, so I said and wrote the wrong thing. I should have been saying 0.4 and I was saying 0.04. So be careful there, that should be a 0 0.4x squared, a 0.4xy, a 0.4xy, and a 0.4y squared. Minus all the same stuff. Kind of a lot of stuff. Let's combine the minus 5,400 and the minus 6,100 to get minus 11,500. Minus 0.03y squared, minus 15y. And then we're going to do our best to combine all the x's and the y's together. It's intriguing to me here. Oh, this is a slightly different question. Yeah, that one's a little bit easier, which is fine. So here, multiplying this all out, or I should say combining like terms, let's look for the x terms first. So I have a 225x. And do I have any other x's? Yes, I do. I have a minus 15x, and I think that's the only x terms. That's going to be a 210x. I think I have the same thing for the y's. 225y. And the only other y term is a minus 15y. That's going to be a 210y. As far as x squared, I have a negative 0.4x. I should use a different color. I have a negative 0.4x squared and a negative 0.05x squared. So I have a negative 0.45x squared. For y, it's a negative, sorry, I'm gonna look at the y squared next, even though I'm kind of skipping these middle terms here. It's a negative 0.4y squared and a negative 0.03y squared. So it's gonna be a negative 0.43y squared. And then I've got these two xy terms here. That's going to combine together to be a negative 0.8 xy. And finally, I've got my minus 11,500. Okay, so there's our simplified down profit function. And now we're going to try to maximize this by the usual methods. Taking the partials, setting them equal to 0, finding the critical points. And then we do want to test them to make sure they actually give us a maximum profit, right? It'd be really terrible if we found the values that actually minimize profit. So it is important that we check to make sure we have the right kind of thing. Typically in these problems, when they ask you to maximize something and you only find one critical point, usually that will be the maximum, but it's still good to check. So let's take our partial derivatives here, which is going to be, it's going to be a little bit funky. This one's going to be a little harder than the one that was done in class. So our partial with respect to x is going to be 210 minus 0.45 times 2 is 0.90 times x. And we also have a negative 0.8 times y. We're going to set that equal to 0. Similarly, our py, our partial with respect to y, is going to be 210 minus 0.86y, and then minus a 0.8x. And so just conceptually here, these two equations are equations of lines, right? Some multiple of x plus some multiple of y equals some constant to each other. And these lines are not parallel to each other, so they're going to cross in one point. Finding the point is going to be a little bit gross. If it were up to me, I'd probably multiply everything by like 100 to have not deal with the decimals. So I might rewrite this as 21,000 minus 90x minus 80y equal to 0. We could have gotten away with multiplying this one by 10, but since this one was going to be 100 as well, I figured I should just do both the same way. This one's going to be 21,000 minus 86y minus 80x equal to 0. And then solving this is never my, like, I have to actually do the work of solving. So yeah, here we go. I'm going to isolate, I guess, x here. So I'm going to have 80x equal to 21,000 minus 86y. So x is equal to 21,000 minus 86y divided by 80. I'm going to substitute that in for x in the other equation. So I'm going to have that 21,000 minus 90 times 21,000 minus 86y over 80 minus 80y is equal to 0. Yeah. So again, I'm going to cancel a 10 there and a 10 there. And then I think I'm going to multiply both sides by 8 to get rid of the denominator, because I don't really want to use denominators. I mean, you could probably like, no, 86 is not divisible by 8. Let's multiply everything by 8. 21,000 times 8 is going to be 168,000. The 8 cancels there, so you get minus 9 times 21,000 minus 86y minus 80y equals 0. Okay, just a lot of fun arithmetic. Good question. It should. Thank you. Yes, maybe I should. You know what that's a good lesson in is actually writing down the thing you're doing and multiplying the entire thing by 8. And yes, 8 times negative 80y should be negative 640y. Thank you very much. Multiplying it out further. Good trick for multiplying by 9 is multiply by 10 and subtract 1. So 9 times 21,000 is 210,000 minus 21,000, which is going to be 189,000. And then 9 times 86 is 860 minus 86, which is going to be 774. Or you can use a calculator. That might be the right thing to do here. Let's see, 72. Yeah, 72 plus 54. Yep, that works. And then combining all the things together, we have 168 minus 189 is going to be 21,000. So negative 21,000. And 774 minus 640 is 134. So we get that y is equal to 21,000 divided by 134, which I guess I can use a calculator to find out. I'm curious about this question here. I want to see one thing. So we're getting that this is approximately 156.7. And I feel like even though, so the problem doesn't say anything about having to have a whole number of units, but sometimes that's kind of what happens. So we might have to round this to the right number of units. Whatever. If we get y equal to that, then we're going to plug back in here, find the x value, and yeesh, I don't really want, so I'm just going to write it in here. So plugging back into either equation, let's plug back into the first one. We have 21,000 minus 90x minus 80 times this terrible y value. And then we could solve for x in the same sort of way. So it looks like 21,000 minus, oh, thank you, sorry, minus 80 times 21,000 over 134 is equal to 90x. So x is some terrible number. 1/90th times. I'm going to factor out the 21,000 as well. 21,000 times 1 minus 80 over 134. I mean, that's not the worst thing I've ever seen in my life, but it's pretty terrible. Let's see what we get. 80 over 134 is the hard part. 1 minus that, and then multiply that by 21,000 divided by 90. We get approximately 94.02. Okay, so that was not particularly fun. But we've got our values, and then we can say, well, do we actually get a maximum? So let's go ahead and find D. D is actually not going to be super terrible here. So looking at our first partials, our D is going to be Pxx, Pyy minus Pxy squared. To be real frank, this is actually the reason I decided to use x's and y instead of x1 and x2. So I really didn't want to write P x1, x1, Py, like it just seemed really, probably not that. Okay. So Pxx is going to be negative 0.9. PYY is going to be negative 0.86. And PXY is going to be negative 0.8. Doesn't matter what our critical point was, right? Because there's nothing to actually plug in. If we calculate this, we have a number. So that number, 0.9 times 0.86, is certainly bigger than 0.8 times 0.8. So this is definitely going to be positive, which means we have a max or a min. And since our PXX is negative, we are concave down, which means we have a maximum. And so you could either use, if you were actually answering this question, you could either use these values, but if you had to round, I'd probably round like up to 157 and down to 94 if we were required to give integer values. So a little bit funky. Yeah. The arithmetic here is certainly kind of not wonderful, but not that, I mean, in the grand scheme of things, not that bad. If you have a calculator on hand, it's pretty manageable. Let's look at one or two more of these, and then we're going to look at one of them in kind of two different contexts. But let's say, because sometimes the problem with these is, like, I feel like that one, they kind of gave it to you straight, like, here's the function, maximize it. Whereas something like, where'd you go? Hiding stuff from myself. Something like the following, find 3 positive numbers, X, Y, and Z, such that, which one's the most interesting here? Sure. Such that the sum is 32 and the product of X, Y squared, Z is minimum. Or they might say something like the sum of the squares is minimum, and they're like, oh yeah, X squared plus Y squared plus Z squared is the thing we're trying to minimize. Or they might say something like, we want to max, oh, sorry, X here, apologies. The sum is 32 and P equal to X, Y squared, Z is maximum. That is, apologies there. So here we have two things going on. We have the thing we want to maximize. So I typically, like, if I'm trying to maximize X, Y squared, Z, if the product, I'm going to write the product is the thing I'm trying to maximize. But really, you can give it any name you want. I saw in her, when she was doing, like, when she was minimizing the sum of the squares, she wrote S equal to X squared plus Y squared plus Z squared, or whatever it was she was doing. And then so we want to maximize this. But we don't have the tools to maximize a function of 3 variables. So we also need a constraint. And our constraint in this problem is that we want the numbers to add up to 32. So X plus Y plus Z equals 32. And I should also point out, we're also limited by the fact that we want all X, Y, and Z to be positive. Usually that's not going to really come into play, but it is important because if X, Y, or Z could be negative, then there wouldn't be an answer to this question. You could pick Y to be a super negative number, and then X and Z to be positive numbers that got you back to 32, and the product would just get larger and larger and larger the more negative you made Y. All right, so then what we usually do is we take this equation, isolate one of the variables, and plug it into this. For me, I wouldn't isolate Y here, because I would prefer not to have to do 32 minus X minus Z squared. So usually you want to pick the thing that's going to be the easiest one to plug into the other equation to solve for. Here, X or Z would make sense. And since we like writing functions of X and Y, I'm going to solve for Z. Z equal to 32 minus X minus Y. And then that is what I'm going to substitute in to that equation there. So then we're trying to maximize the product as a function of X and Y, which is X times Y squared times 32 minus X minus Y. I can see that I'm going to have to use the product rule here, but if I think of it as just this piece times this piece, it's only a single, it's not like a triple product rule. So let's find our partial derivatives. Px is going to be y squared. I should, no, I've already finished. So I would say, even though I'm using the product rule here, it probably would have been better just to multiply it out. Multiplying it out is not that hard. Right? This multiplies out as 32xy squared minus x squared y squared minus xy cubed. Probably the better way. But I'm doing it this way, so using the product rule, you're going to get y squared times the not derivative of that stuff plus now xy squared times the derivative of that, which is negative 1. And set that equal to 0. Similarly, for the partial with respect to y, we're going to get 2xy times 32 minus x minus y plus xy squared times also negative 1. Usually, if I'm trying to solve these equations, I'm thinking about factoring stuff out if I can. So for this first equation, I see that I can factor out a y squared. So I'm going to rewrite also y squared times 32 minus x minus y, and then I have an x times a negative 1, which is a minus 2x. Over here, I see that I can factor out an x times a y. And I'm left with 2 times 32 minus x minus y. Let's multiply that 2 through. You get 64 minus 2x minus 2y. And here, I factored out the xy. I'm still left with a y times a negative 1. So a minus y. So interesting. Yeah, this is good. So this requires a little bit of work. So simplifying this a little bit further, we have y squared times 32 minus 3x minus y equal to 0. And this one, simplifying that a little bit more, we have x times y times 64 minus 2x minus 3y equal to 0. Now, normally I would say we have to look at y equals 0 and x equals 0 as potential critical points, but we don't need to here because we were given the requirement that all the numbers have to be positive. Right? We definitely can't maximize the product if any of those numbers are 0. So we can kind of we can leave those behind and say, well, I don't care about setting that equal to 0. I just care about setting this equal to 0 and this equal to 0. And again, we're kind of in the same situation we were before. We've got 2 lines. We can certainly find the point where they intersect. Let's do this one slightly differently than we did the last one. So here are the 2 line equations that I would like both to equal to end up to find the point of intersection for. 32 minus 3x minus y equals 0, and 64 minus 2x minus 3y equal to 0. And what I would probably do is multiply this first equation by -3, and then add those 2 equations together so that the y's cancel. So if I multiply this by -3, I'm going to get -96 plus 9x plus 3y equal to 0. And down here, I still have 64 minus 2x minus 3y equal to 0. If I add those together, I get -96 plus 64. I get 9x plus -2x. And I get 3y plus -3y, which is 0. And then it's equal to 0. And then we can solve for x. And we get x equal to positive 32 divided by 7. And then we go back. Actually, you know what? Instead of going back, we could go back and plug this in and find what y is, but then you still have to like multiply fractions. The actual easier way to go is then just to do the same kind of thing and eliminate the x instead of eliminate the y. So if we do that here, we multiply that equation by a -2 and get -64 plus 6x plus 2y equal to 0, and multiply this other equation by +3, get 192 minus 6x minus 9y equal to 0. Add those together, then we get 128 plus 0x minus 7y equal to 0. End up with y equal to 128 over 7. we have two things left to do still. We have to find Z. We also have to verify that it's giving us a maximum. So if we look back at our first partials, yeah, I definitely went the harder way of doing this, I think, by using the product rule. But if I look at this here, here's my PX, there's my PY. I do think it's worth multiplying it out. So PX is 32y squared minus 3xy squared minus y cubed. And PY is 64xy minus 2x squared y minus 3xy squared. PXX is going to be just a negative 3y squared. PYY is going to be a 64x minus 2x squared minus 6xy. Kind of gnarly. And then a PXY is going to be 64y minus 6xy minus 3y squared. Ugh. So then our capital D is really kind of gross. Our capital D is going to be negative 3y squared times all that, 64x minus 2x squared minus 6xy minus all that squared. And then you have to plug in those points. Yeesh. Okay, so I'm really not thrilled about this. Let's just say we did it. And so here's what should happen. So when we've done everything right, we should plug X and Y into each place it needs to go. And this should be greater than 0. And then we'll notice that easily we can notice that PXX here has to be negative because it's negative 3 times whatever y squared is, which means we're concave down, which means we have a maximum at X equal to 32 over 7, Y equal to 128 over 7. And if we go back and look at the original constraint, we know that Z should equal 32 minus X minus Y. So Z is equal to 32 minus 32 over 7 minus 128 over 7. And I guess if we wanted to simplify that, 32 times 7 over 7 is 224 over 7. Minus 32 minus 128 over 7 comes out to be, I don't know. Let's see, that's 160. So that's going to be 64 over 7. So here's why I find this answer concerning. If you look at the original equation, we're trying to maximize X times Y squared times Z. To me, it seems X and Z should end up having the same value. There's no good reason that X and Z should be different. It makes me feel like our answer is wrong. Don't love. Or I mean, the better phrase there is it makes me feel like I made an error somewhere when I was calculating X or Y. Yeah, 32 over 7. Oh no, I think I'm making a mistake right here, actually. It's 4/7. That's 1. So here's okay. I'm seeing this as 4 times 32/7. And I'm seeing this as 1 times 32/7. If we have to add the 32, there's 2 times 32/7 left over. I feel like I made an error somewhere, which is disappointing because it's a lot of work. Bummer. Yeah, I don't want to spend our time looking at it. So I'm gonna look at this later and see if I can figure out if I made a mistake or if I'm pretty confident I made a mistake though, because really, if you are maximizing something like this, X and Z should be the same, right? There's nothing about this constraint that looks to me that X and Z should be any different than each other. So I'm really, really confident that X and Z should be the same. I'm gonna work this out later, see if I can figure out what I did. But the process is still terrible. Let's look at one more. I think we have enough time to look at it in both ways I want to look at it. So one more thing. This is a pretty standard question. It gets asked in this section. It's about mailing a box. We want to find the dimensions of the largest rectangular package that can be mailed with the requirement that the length of the box plus the girth of the box is less than or equal to 144 inches. I think it's actually a pretty standard requirement of measurement, like that the length plus the girth doesn't exceed some number. I don't know. Yeah, but like, I think I believe it is actually a real thing that mailing services try to limit, so that basically so that the box fits in some way, but also isn't too giant. So if we draw a picture of our box, we're always, at least I'm always imagining the length as the longest dimension. So I'm thinking of this part here as the length. Let's call this Z. So our length is Z, and the girth is the around measurement in the other direction. So basically the girth is going to be this measurement here. And if we call this side X and this side Y, then the girth is going to be 2 times X plus 2 times Y. So we would like to find the largest box, meaning the box that holds the most volume. So we want to maximize volume, which is X times Y times Z. And our constraint is that the length plus the girth, so 2X plus 2Y plus Z, is less than or equal to 144 inches. But if we actually want to maximize the volume, we're going to use all of that constraint. So we're going to set it equal to 144 inches. And then just like every other time, we're going to isolate one of these variables, typically the one that's Z, unless there's a really good reason not to pick Z. So Z equals 144 minus 2X minus 2Y, and we're going to substitute that back into our other thing here. So our volume as a function of just X and Y is going to be X times Y times 144 minus 2X minus 2Y. And I make the smarter choice this time and actually multiply it out. Get 144xy minus 2x squared y minus 2xy squared. Yeah. So finding our partials, Vx is 144y minus 4xy minus 2y squared equals 0. Vy is going to be very similar. It's going to be 144x minus 2x squared minus 4xy. Each equation we can factor out one of the variables. So the first equation, we're going to factor out the y. We're left with 144 minus 4x minus 2y, 0. Similarly here, we're factoring out the x, and we're left with 144 minus 2x minus 4y. We can also factor out the 2. I did not think about that, but yes, we could factor out a 2 as well. Does that seem all right?
I was just looking at this. I'm not like physically could set one, multiply 1 by -1 and then cancel out the this one.
Oh, sure. Yeah. Yeah, but I don't know if that actually helps us. We're seeing the same thing we've seen the last 2, where we don't really care about X or Y being 0, because again, we're trying to maximize the volume of this shape. So we're going to set this equal to 0, and this equal to 0, and then we're going to try to solve that system. This one's not too terrible. So we set 144 minus 4x minus 2y equal to 0. I'm just going to say that I have 144 minus 4x equal to 2y. And then we take the other equation, 144 minus 2x minus 4y equal to 0, and replace the 2y with that. So 144 minus 2x minus 2 times 2y, right? Because that's a 4y. So I'm just going to plug in that right there. So then simplifying, we get 144 minus 2x minus 288 plus 8x equal to 0. 8x minus 2x is 6x. 144 minus 288 is negative 144. Add it to the other side, you get positive 144. So x is going to be 144 divided by 6, which is 24. Y is going to be the same, which is, again, isn't surprising if you look at our, right? So this one, I think to me, it seems again obvious that if your constraint has 2x and 2y being the same, and your volume has x and y being the same, you're typically going to get x and y to be the same as each other. And we're definitely going to get that here. If you plug this back into this equation here, then 2y is equal to 144 minus 4 times 24. So 2y is equal to 144 minus 96 is 48. Excuse me, y equal to 24. We can test to make sure that we have a maximum. So looking at our Vx and our Vy, my D, which is Vxx times Vyy minus Vxy squared, is going to equal, see, Vxx is going to be 0 minus 4y minus 0. Vyy is going to be 0 minus 0 minus 4x. And Vxy is going to be 144 minus 4x minus 4y squared. And if we plug in our 24 comma 24, we're going to get negative 4 times 24 times negative 4 times 24 minus 144 minus 4 times 24 is 96 minus 96 squared. And this number here is, well, 144 minus 96 is 48, minus another 96 is negative 48. And certainly 96 squared is bigger than 48 squared. So that's going to be positive. And since this is negative, we again have a maximum. I feel like all these have been maximum. Sorry, it's a little boring. They're all the same. So concave down, maximum. And then we go back and find Z, and we see that Z is equal to 144 minus 2x minus 2y. That's 144 minus 48 minus 48, which ends up being also 48. No, sorry, not also, just 48. So the dimensions of our largest box that meets the requirement is 24 inches by 24 inches by 48 inches. So now we do the same problem in a different way. Unless you need to go.
Yeah,
Okay, if you need to go, you should. If you need to go, you can, and you, especially if you're the only one here. Be like, hey James, I need to go. You're welcome. Well, we'll talk about that on Friday. So the other way is using LaGrange multipliers.
Oh yeah, we have not.
Right, which is why I was kind of like saving until the end.
Thank you.
You're welcome. See you on Friday. Yeah, I'm gonna do this problem though, using the LaGrange multipliers right now. So here's how we do using the LaGrange multipliers. We still want to maximize the volume, which is x times y times z. And our constraint is still 2x plus 2y plus z equal to 144. And a lot of times in this class, we rewrite the constraint so it's equal to 0. So you can write it this way, or you can write it as 2x plus 2y plus z minus 144 equal to 0. And then we set up this new function. I think we use a capital F of x comma y comma z comma lambda, where lambda is the LaGrange multiplier. And that function is equal to your thing you want to maximize, which you usually call little f, minus lambda times our constraint, which we usually call little g, which without the 0 part. So it's going to be lambda times 2x plus 2y plus z minus 144. And then we're going to find all the partial derivatives and set them equal to 0. And again, not again. The reason why this kind of works is you're essentially seeing where both things get maximized at the same time. So our capital Fx is going to be y times z minus the constant, lambda is a constant, although it's acting like a variable. And then, well, I should say for x, it's a constant. The derivative of 2x is just 2. Fy is going to be xz minus lambda times 2. Fz is going to be xy minus lambda times 1. And finally, although I don't think you need to write this one down, you're going to have f lambda, which is just the derivative of this. So the derivative of minus lambda is minus 1 times all of this is a constant. But if you notice, this is really, we set this equal to 0. If you multiply this as a negative 1, this is just 2x plus 2y plus z minus 144 equal to 0. That's just your constraint again. So I don't think you actually need to write this one down because you already have it right there. And then the whole point of this is you want to try to figure out x, y, and z are. There's a number of ways to do this. Usually, here's what I would do. So I would solve each equation for lambda. So I would say, great. I can write this here. So I'm going to get lambda equal to yz divided by 2. Here I'm going to get lambda equal to xz divided by 2. And here I'm going to get lambda equal to xy. And then we set these equal to each other. So if I set the first two equal to each other, I'm going to get yz over 2 equal to xz over 2. If we multiply both sides by 2 and divide both sides by z, we end up getting x equal to y. And then if we pick a different two, like these two equal to each other, we're going to get xy equal to xz over 2. Multiplying both sides by, or say dividing both sides by x, we get y equal to z over 2, or 1/2 z. And then whichever variable is showing up both times, in this case y, we isolate y. So if I had like 2y equal to z, I would then divide both sides by 2 to get y equal to 1/2 z. And then we plug each of those into the constraint. So our constraint, which was 2x plus 2y plus z equal to 144. Now we're going to plug in. Ooh, I said that part wrong before. I can't plug in this for y and this for y. We actually do want to solve the other way. We want to solve, so if y shows up twice, we want to solve each thing in terms of y, meaning I want z equal to 2y, and here I want x equal to y. So then if I plug in 2y for z and y for x, I end up with 2y plus 2y plus 2y equal to 144. So when you do this, you essentially take your equation that has 3 variables in it and get an equation with 1 variable in it by writing both z in terms of y and x in terms of y. And then that becomes 6y equals 144, which then becomes y equal to 24, just like last time. And then x equals y, so x also equals 24. And then z equals 2y, so z equals 2 times 24, which is 48. We get the exact same values we got from before. The one downside, one of the downsides to LaGrange multipliers is it's not immediately obvious, or you can't do a test to see if it's a maximum or minimum. You just have to kind of convince yourself that it's the thing that you need it to be. All right, that's all I got.